So anytime we have a force that is going in multiple directions, we break them into X and Y components, and we already know what we're talking about here. So this would look like this. If I was applying a force upward at an angle of 30 degrees, right? And let's say that we applied this force of 400 newtons. That means that I would need to break this force into its Y component and its X component. Okay, and so for the Y component here, would I use sine or cosine? For Y, I would use sine, and for X, I would use cosine. And then after I break that into components, I'm done with that 400. I'm not going to use that anymore. Right? Once I'm done with breaking it into its components, I would only use this Y side or this X side in my net force equation, depending on what it called for. Okay, so that's really all we're doing here with these types of forces. The thing that's going to change for us most specifically is typically the normal force. So I want to think about an example like this. When my object is just at rest, I've got the gravitational force and normal force. So let's say that I have a book resting on a table. If it's at rest and it's the only forces like this, what do we know about our normal force and our gravitational force? They're congruent. They're equal to each other, right? They offset. But now if I have an object that's sitting and I'm pulling upward on it, I still have a normal force, right? This is still my normal force. This is still my gravitational force. I've got some pulling force upward here. Is my normal force just going to be equal to my gravitational force in this case? It's not. Think about it. I'm lifting up on the object a little bit, right? So the normal force does not have to work as hard. What we know about this force at an angle is that it has an X and a Y component. So if I'm looking at my vertical forces, I have 1, 2, 3 vertical forces. And I know that these two combined must equal that one, right? If my object is at rest vertically there. So we're going to go into some problems that show us that. But I want to see as we start applying things at an angle, it's really going to affect the normal force. That's the thing that's going to change the most, is that it's not going to be as big as it typically is. Okay. So let's go ahead and look at this one. It says a force of 2,000 newtons acting at an angle of 60 degrees with respect to the horizontal is exerted on a car. So let's go ahead and draw our diagram here. We've got our gravitational force. Can you see that yellow okay? Okay. We've got our normal force, because although we're towing the car, isn't it still on the ground? Right? We're just pulling upward on it at an angle. So we might call this force pull. We could call it tension because it's probably being pulled with a cable of some sort. It's not that big of a deal one way or the other, but we're going to call it there. And our 60 degrees says with respect to the horizontal. And so all that means is that here's our horizontal, right here, our horizontal line. And so the 60 degrees is just upward from that. So our 60 degrees fits right in here, 60 degrees. Okay, and of course we'll break this into its X and its Y component. I might call this force pull Y and force pull X. Okay, our goal, it says it's accelerated from rest at 10 meters per second squared. Find the mass of the car. So our goal is to find mass. Okay. The first question that we have to kind of ask ourselves here is the acceleration that the car is experiencing horizontal or vertical? Horizontal, right? It's not lifting the car up at 10 meters per second squared. It's moving it forward, right? It's dragging it forward. So our acceleration is horizontal. What component of the force will we be working with? Are we focusing here then? If our acceleration is horizontal, are we concerned with our horizontal forces or the vertical forces? Horizontal. So that means I'm really only working with this force right here. So I'm going to go ahead and solve that. Let's go ahead and solve for what is FPX equal to, right? In this case, the pulling force is, did it tell us? 2,000 newtons. So I would take 2,000 times cosine of 60, and I get 1,000 newtons as the component of that force. We agree there? Right, that's the X component. And so if I look at my situation here, I only have one force acting in the horizontal direction. So I need to set up my net force equation as force pull X, because this is my only horizontal force here. And I could write in a -0, so I know I kind of thought about the fact there's nothing opposing that, but I don't have to write that in. Okay, now I can start putting in numbers. What do we sub in for F net? What's another alternate way for us to solve for the net force? Mass times acceleration. So the mass is what we're solving for. The acceleration they told us was 10, and the X component of that force is 1,000. So that means my mass is 100 kilograms. So it must be like a clown car or something. Right? It's a little Tykes car. Okay, not very heavy. Does that kind of make sense? Right? The only thing we had to do is break that applied force down into its components because it was being applied at an angle. Right? We can't work with things at angles. And then you'll notice we didn't use the 2,000 anywhere in the problem. Right? Once that's broken down, we're going to be done with that. Yeah.
How did you know?
So once we start looking at our diagram, we're going to decide, are we really focusing on the vertical forces or the horizontal forces? Once we decide that, then we set up a net force equation that is any positive forces added together, and we're going to take out any forces that are going in the negative direction. So this template of positive forces minus negative forces is going to be how we start all of our problems, really. Okay, I call this the net force equation, and that just puts anything that's going in the positive direction, which this one was, minus anything that's going in the negative direction, which there wasn't anything there. So that's why I put the -0. You don't have to write the -0 necessarily, but it helps you think about it. Okay, but this is going to be what we do for vertical systems too. So let's just look at this problem and think about if I was going to set up the net force equation for vertical, F net in the y direction, what would the equation look like? How many forces do I have in the y direction? Can you name them? How many do I have? Normal force would be 1. FPY would be 1. What would be the third one? FG. So my equation in this case would be normal force plus FPY, and I add those because they're both going in the positive direction, minus FG. Right, minus FG. So that setting up this system is really, really, really important. Okay, our problems have to start with the free body diagram, and then we'll often head this way, right, to having that equation. All right, let's look at another one here. It says a 50-kilogram washing machine is being lifted upward with a force of 200 newtons at an angle of 40 degrees to the horizontal. The machine begins to slide. That's a really important context clue. It might not seem like it, but it's really important because what does that tell us?
Gravity's heavy. Gravity has more force.
Yes, it tells us it's not leaving the ground, right? It tells us that it's not accelerating vertically. It's only moving horizontally, right? We're lifting it, we're pulling it, but it's just being dragged, right? Okay. Find the normal force acting on the washing machine. So let's start with our free body diagram. Okay, can you see the purple on the black? I'm worried that's hard for you to see. Is it okay? Okay. So here's our free body diagram. I've got gravity. I've got the normal force. I've got an applied force here. And it doesn't tell me anything about friction or anything like that, so I get to leave everything else off. So let's go ahead and label them. This is the normal force, and this I might call force pull. Whatever I want to call that one is not that big of a deal. In this case, can you tell me, is the normal force going to automatically equal the gravitational force? It's not. It's not because I've got another force that's interfering with that, right? If they're the only two vertical forces, then yeah, they're probably going to be equal. But I have something else interfering with that. So that's not going to be the case. Let's go ahead and look at the components here. If our goal is to find the normal force, do I need both sets of components or do I just need the vertical component? I really just need the vertical component, right? There's my 40 degrees. We're going to call this force of the pull in the y direction. The pulling force was 200 newtons. Okay, so to find the y force, I would take 200 times sine of 40, and I get 128.6 newtons. So let's go ahead and, can I solve for my FG right now? Remind me, how do I find the weight of my object? How do I find FG? We wrote that on our equation sheet. Mass times gravity. So I would take mass, 50 times 9.8, and I get 490 newtons. And we don't know the normal force, right? We can't do anything there. That's our goal. So let's go ahead and set up our net force equation here. F net, and you could write a little y there to show that you're dealing with the vertical things. That's not a necessity, but you could. And so I'm going to add up anything that's going upward, normal force, plus FPY minus FG. And we already know some of those numbers, but I think it's a good practice to get the equation written out first. So now let's go ahead and start putting in our numbers here. Is my object accelerating in the vertical direction? It's not, right? It's just sliding. So what does that mean? My net force is going to be equal to 0, right? Because it'd be the same if I plugged in mass times 0 for acceleration, right? It would be 0, so I don't need to bother putting it, right? It's not moving vertically, so that's 0. Normal force is what I'm solving for. This is 128.6, and this is 490, right? We just subbed in the numbers we have for those variables. So now I'm just going to take 128.6 minus 490, and then I would add that to the other side, right? 0 equals normal force minus 361.4. I would add that over. So my normal force is equal to 361.4 newtons. Uh-huh.
So if you
Here's our applied force, which is 40 newtons at an angle of 33 degrees. Okay, we might call this force, I don't know, pull Y, force pull X. And am I going to need both the X and the Y component for this problem?
no, just the X. Oh, yeah,
Doesn't it ask us for the normal force and the horizontal acceleration? So we will eventually need both of them. We can't use them both in the same equation, but we will need both. So let's go ahead and solve both so that we know. So 40 sine 33 and 40 cosine 33. Please go ahead and plug these into your calculator so we get really good at doing that. There's a difference in you doing it versus you watching me. So for Y, I got 21.8. And for X, I got 33.5. Does it matter to us now the order that we solve these in? Do we have to find normal force first, or do we have to find horizontal acceleration first? For this problem, it really doesn't matter, right? Because they're independent of one another for right now. Okay, so if I was going to solve for the normal force, would it be congruent to the gravitational force? Are these two congruent in this problem? They're not. But what do I know about the normal force? It's going to be positive. Yes?
Minus the 21.8 from the gravity.
Yeah, right. It's going to, the normal force combined with the y have to equal gravity. Okay, so let's go ahead and solve to find out what is gravity here. Gravity is mass times, the gravitational force is mass times the acceleration of gravity, so 84 times 9.8 gives us 823.2 newtons is the weight, Fg. And so I know in this case, the normal force, Fn plus Fpy minus Fg, all of those vertical forces are my net force. And in this scenario, I know my net force is equal to 0, right? Normal plus 21.8 minus 823.2. And so my normal force comes out to be 801.4 newtons. And does that answer seem reasonable in terms of our problem, right? Because if there was nothing else acting, our normal force would have been 823.2. But we're taking some pressure off of it, right? We're lifting upward, so the normal force does not have to do as much. So we expected it to go down a little bit, which it did. Okay? And then how about horizontal acceleration? What would that net force equation look like? F net in the x direction this time would just be force of the push x component. And do I have anything opposing it? No. So I can put the minus 0 or I can leave it off. But we're just going to say 33.5 is my net force, which is equal to the mass times the acceleration. So 33.5 divided by 84 gives me an acceleration of 0.4 meters per second squared. That's a little rounding, but that's fine. So it says it's moving to the right, but how is it moving? Is it accelerating to the right?
Constant velocity.
Okay, that's our key word there. Constant velocity. That's going to be really, really, really important. If we have constant velocity, what does that mean is true about our acceleration? Our acceleration is equal to 0. 0, right? If I have constant velocity, I don't have any acceleration. If I have constant velocity, my net force is 0 because my acceleration is 0. And so if I have constant velocity in the horizontal direction, that must mean, since I only have two forces acting, these two forces are congruent, right? Because I'm moving at constant velocity, my positive and my negative forces have to cancel each other out. And so if that is true, that's congruent. That makes this 50 newtons. And so now I'm able to just do trigonometry and know that if my cosine or my adjacent side is 50, I can solve for my hypotenuse. Do we see how that works? So I would just plug it in like this. Cosine of 34 is equal to the adjacent side over the hypotenuse. So I could rearrange that to say my hypotenuse is equal to 50 divided by cosine 34. So let's go ahead and plug that in and see what we get. Oh, something's not right there. What did I do wrong? $50 divided by cosine 34. Okay, 60.3 newtons. Okay, there we go. Does that make sense? Should our force there, should it have come out greater than 50? Yeah, it had to be, right? Hypotenuse can't be shorter than the leg of our triangle. That's number one, right? And I'm having to work harder to overcome friction because I'm pulling at an angle, right? If I was pulling purely horizontally, I would only have to apply 50 newtons of force to overcome friction. But because I'm pulling at an angle, I have to work a little bit harder. I have to apply more force to make that happen. Okay, try this one on your own. It says a 407 Newton cart is being pulled to the left by a force of 400 newtons at 28 degrees. What is the normal force and acceleration, normal force and horizontal acceleration, if there is 28 newtons of friction?
What do you mean by the cart being 407 newtons?
Okay, great question. This is different than saying it's 407 kilograms, right? This being already measured in newtons, that means that is already Fg. It's like we already took mass times gravity, and that's the result, is 407. Does that make sense for everybody? It's given in newtons, which means that is equal to the weight already. So if you need mass later, how might you get rid of that? Divide it by 9.8. Right, good. Okay, go ahead and see where you're getting. I'm going to freeze it, and I'll get it worked up here, and then we'll see. We'll kind of check as we go here. Yeah, no, you're right. You're right. I dropped my negative, and I shouldn't have. This should be negative 7.84. Yeah, sorry about that. Because the result of that is a negative 325. So when I divide it by 41, I'm going to get negative 7. Yep. Thank you.